After the virtual field trip focused on the Chapea outcrop, let's give a look to some other outcrops. These virtual field trips target people involved in a reservoir fracture study but not familiar with geology. Let me stress that caution must be utilized with what we can see on outcrops, because fracture system exposed, affected by late-acting process like unloading and weathering, are bound to be different from the fracture system of the reservoir, which are located at several thousand meters burial depth. However, outcrops can certainly give some insight on the possible characteristics and complexity of the fracture network affecting the flow path in the producing field. So let's move from the outcrops of the former virtual field trip, located just in front of the Ligurian Sea and relevant to the Antola unit, to a different geological context that are the Alps. Moving northwestward, we fly over the Apennine Mountains, then we cross the Po Valley to pass over the Italian Prealps and reach the area where we are going to focus the attention, an area called the Alpage du Rawill, or, more geologically, the Rawill Axial Depression. In particular, the targets are the extended outcrops of carbonate rocks that are present in this zone. These outcrops are located in Switzerland along the southern flank of the Schneiderhorn Peak at an altitude ranging between 2,400 and 3,000 meters above the sea level, at the border between the canton of Valais and Bern. The value of these outcrops is given by their characteristics: Cretaceous carbonate platform sediment representing the reservoir rock of many gas and oil fields worldwide, and by the possibility to observe fractures on very extended horizontal pavements. Geographically, the outcrops are located along the mountain pathway that connect the Wildstrubel Peak with the Wildhorn Peak, between the Rawill Pass and the Lake of Thennet, just northward of the Rhone River Valley, between the towns of Sierre southward and Gstaad northward. Here we are in a quite different geological context with respect to the Chapea outcrops of the former virtual field trip. In fact, we are making a very long jump of about 260 kilometers northwards, crossing the Po Valley, moving from the northern Apennine to the western Alps. A big jump crossing a very complex geological context, as summarized by the geological map on the left and by the cross-section at the top right, to land in an area known as the Rawill Axial Depression. Actually, we are going to focus the attention just on a carbonate formation belonging to the Helvetic nappes, that are a component of the very complex structural framework of the Western Alps. Of course, the understanding of the fracture network characteristics affecting the flow in a reservoir call for an understanding of the geological stresses affecting along the time the rock. So, before focusing the attention on the outcrops, let's try to summarize some basic background information about the relevant geological context. We are going to focus the attention on the outcrops of the carbonate Urgonian Schrattenkalk formation, late Barremian to early Aptian in age, as here illustrated by the lithostratigraphic log of the sedimentary succession outcropping in the area. In this time gap, two phases of platform development have been recognized: the lower and upper Schartenkalk, which were interrupted by a phase of increased detrital input, the Rawill member. The lower Schartenkalk is composed of approximately 150 meters of bioclastic and oolitic limestone, which includes increasing amounts of rhodist and coral remains toward the top. The Rawill member consists of approximately 20 meters of well-bedded limestone and marly limestone. The upper Schartenkalk is represented by 30-50 meters of coarsely bedded bioclastic limestone, which is again rich in rhodist and corals toward the top. They represent sedimentary remains of a vast shallow water carbonate platform, attached to the northern Tethyan shelf and presently locked up in the Helvetic Alps. During the evolution of this platform, a phase of an important regional platform progradation and aggradation has been recognized, which resulted in the build-up of a prominent and predominantly photozone carbonate succession, the so-called Urgonian platform. Coeval sediment of equivalent or at least comparable features are largely present in the southern Mediterranean Sea and in the Middle East, where they represent very important reservoirs for the oil and gas industry. So the Schartenkalk formation could represent an interesting analog for several oil and gas fields developed in those areas. Magnifying and focusing on the area to be analyzed, we can see that the outcrops of the Schartenkalk formation are quite extended, as highlighted by the light green color in the geological map. However, these outcrops are located in a geological context very complex because of the structural history affecting this area. In fact, the fracture network observed in any formation is bounded to mirror the stresses the rock underwent along its geological history. In this specific case, the different tectonic events affecting the carbonate Urgonian Schartenkalk formation are the tectonic event of the Western Alps. Targeting these field trips people like reservoir engineers without a geological background, a short description of these amazing geological events can be very useful to understand the possible complexity of the geology that can affect the reservoirs of the oil and gas fields. Of course, the short summary that I'm going to make is very simplified, let's say just informative, a topic to be deepened in case on the basis of the papers published, some of them listed in the reference at the end of this field trip presentation, papers you are strongly recommended to refer to. So let's start making the list of the four main events that defined, along the time, the building of the Western Alps. The Pangea breaking, finalized in the Lower Jurassic, followed by the Alpine Tethys rifting, followed in the Middle Cretaceous by the beginning of the European plate subduction below the Apulian plate, up to the collision of the two plates, the European and the Apulian plates. Let's start focusing the attention on the first event, that is the Pangea breaking. About 200 million years ago, in the Triassic period, the Pangea continent started breaking in two continents because of extensional forces related to the convective currents of the mantle. The continent located northward is named Laurasia, while that one located southward is named Gondwana. Now, focusing the attention on the areas that will give origin to the Western Alps, we can recognize the estimated limits between these two continents before the Pangea breaking, as well as some black lines depicting the position at that time of the present geographic regions like the coastline of Spain and of northwestward France, and of the Corsica, Sardinia and Sicily Island, and the Adriatic Sea. The Tethys Sea advanced toward the west, insinuating itself into the rift of the Pangea breaking due to the extensional forces related to the rising of the asthenosphere. Let's move to the following event, that is the Alpine Tethys rifting. Below the Pangea breaking zone, the asthenosphere arcs and approaches the Earth's surface, feeding the middle ocean ridge with basaltic magma and so producing new oceanic crust between the two continents that are moving away. The crustal extension creates, at both continent edges, large normal fault that define the gradual lowering of the margin, while at their back a symmetric uplift is triggered, creating the so-called rift shoulders and the relevant breccias resulting from the erosion of the rift shoulders mountains. The presence of these Jurassic breccias also along the Atlantic shores proves the simultaneous opening of the Central Atlantic Ocean and the Tethys. So at this time we have from one side the Apulia and Africa plates moving together southwards, while from the other side the America, the Iberia and European plates moving all together northwards. During Jurassic time, because of the gradual moving away of the two continents from the middle ocean ridge where the asthenosphere arcs, the formerly uplifted rift shoulders are affected by subsidence, and the Tethys Sea largely transgress over the two continents, both northwards and southwards. In fact, the Central Atlantic and the Tethys represented a kind of east-west oriented ocean that has been named locally in our area of interest as Piemontese. The southern margin of the European continent is at this time linked to the small Iberian plate that in our area of interest is characterized by a kind of thin ridge named Brianzonese. The Brianzonese was at that time uplifted, sometime above the sea level, as the Jurassic stratigraphic sedimentation sequence suggests, being affected by mist or condensate intervals. The sea extension largely exceeded the oceanic crust. It is estimated that in this area the height of the oceanic crust could range between 1,000 and 2,000 kilometers, and more than 3,000 kilometers the height of the Tethys Sea that overflowed on the continental crust. Let's move to the following event, that is the Alpine Tethys subduction. In Cretaceous period, several things happened. The Central Atlantic proceeded to open. The Southern Atlantic started a quite fast opening process with a separation between South America and Africa. Africa that was rotating counterclockwise, while the Northern Atlantic started a slow rifting. In the meantime, the Iberian plate detached from Europe, creating in between a new ocean named Valesano, narrow and elongated east-westward from the Alpine to the Pyrenees future area. This sea overflowed the southern European continental crust and similar sedimentary conditions were created all over its shore, as highlighted by the similar Cretaceous carbonate platform sediment named Urgonian, recognized in the Alpine and Pyrenean stratigraphic sequence, carbonate platform that is the target of this virtual field trip. In the meantime, the Apulian plate started moving northwestward faster than Africa, and the Piemontese Ocean in between, the Iberian plate moving southward and the Apulian plate moving northward, started the subduction below the Apulian plate that had become an active margin. As a consequence, the Piemontese Ocean started disappearing by subduction, while the Valaisan Ocean northward was still in an extension regime. Along the Apulian plate northern margin, the process of subduction creates an accretionary prism made of extended oceanic crust fragments escaping from subduction. The accretionary prism is made mainly by the oceanic sediments consisting of rock relatively lighter and so sometimes escaping from subduction by a kind of buoyancy. The process so accumulates large slabs of coastal rocks at the base of the accretionary prism that is made by southern rocks gradually overlapping the more northern rocks. It is like a kind of snow blower gradually accumulating the snow on top of the older, farther snow. It is a process that happens in geological times and so bound to overlaps older rocks on top of younger rocks. So, while southward, at the northern margin of the Apulian plate, the subduction started, northward, on the southern margin of the European plate, the conditions were favorable for the settlement of a vast shallow water carbonate platform, the so-called Urgonian platform. It is in this context that the Shorten Calc formation, final target of this virtual field trip, sedimented. Let's move to the following event, that is, the collision. After more than 50 million of years of subduction, the Piemontese Ocean disappears, only in part preserved inside the accretionary prism. Now is the southern margin of the Brianzonese continental crust that started to be involved in the subduction, while the Valaisan Ocean stopped its expansion. Both the Helvetic and Austalpine areas are uplifted, emerged, affected by erosion producing bridges. In the following 10 million of years, the subduction below the Apulian plate swallowed the rocks of both the Brianzonese and Valaisan Ocean. Now the accretionary prism includes, piled one under the other, the remains of the northern margin of the Austalpine domain, above the remain of the Piemontese Ocean, in turn above the Brianzonese, in turn above the Valaisano Ocean. The later three, Piemontese, Brianzonese and Valaisano, grouped all together, are named by geologists as Penninic. Now, even the southern margin of the European plate starts to be affected by the subduction, with the involvement of its continental crust that collide with the accretionary prism, becoming an orogenic prism. Northward, in the Helvetic domain, the conditions are favorable for the sedimentation of the nummulitic limestone. In the following 5 million of years, the subduction of the European plate proceeded, with the thickening of the continental crust that, at high depth, underwent to very high pressure and temperature conditions, making the rocks very ductile. With this condition, the rocks included in the orogenic prism were largely deformed, banded, and sometimes metamorphosed. Southward, the Australpine start to overthrust the Penninic domain with the formation of the Australpine nappes. In the following 10 million of years, the collision between Europe and Apulia proceeded with the uplift of the orogenic prism and the overthrust of the Australpine domain over the Penninic domain, with the increased extension of the Australpine nappes covering all the Penninic domain. While northwards, we have the formation of the Helvetic nappes. The continuous thickening of the orogenic prism, incorporating more and more elements made mainly by lighter sedimentary rocks, hinders, due to buoyancy, the subduction of the European plate that breaks in two parts. The heavier proceeds subduction, while the lighter is largely bended and uplifted. This event contributed to accelerate the uplift of the orogenic prism with the formation of mountains where the shallow unit were mainly the Australpine nappes. Therefore, their erosion started filling northward the foreland Molassa basin. In the following 25 million of years, up to the present time, the collision between the European and Apulian plates proceed with the uplift of the mountains, balanced by their erosion that largely affect the most shallow unit that were the Australpine. It is estimated that the Australpine building had originally a thickness of about 20,000 meters that have been, along the time, affected by uplift balanced by the erosion. Because of this erosion, the Australpine nappes almost disappeared, and both the underlying Penninic and Helvetic nappes are now largely exposed. This 3D sketch shows the Alpine building characterized by the northwestward verging anticline, presenting an axial depression. It is in this depression that the rocks of the highest nappes are preserved by the erosion, like the Australpine Dent Blanche and Materon clip, and the Helvetic nappes in the Rawill axial depression. In this last area, the target of this virtual field trip, the Helvetic nappes are preserved, while laterally, along this anticline axis, are eroded, southwestward on top of the Mont Blanc Massif, and northeastward on top of Haar Massif. An example of this complex alpine building can be observed just southward of our area of interest, on the other flank of the Rhone Valley, where the piling up of the different nappes can be observed. So, moving from the Rawill Alpage and going southward, upward the lateral valley of Anivière, we can climb to the mountain's ridge overhanging the village of Grimens. From here, looking southeastward, we can observe from this point of view the piling up of the different nappes. The tar from south to north, the Apulian plate, yellow in the sketch, overlying the rocks blue and dark, relevant to the Piemontese Ocean, in turn overlying the rock pink in the sketch, relevant to the Brianzonese and the European plate. So we have oceanic crust in between continental crust belonging to different plates. Moving northward, just on the other side of the Rhone Valley, we go back to our area of interest that is characterized by the presence of the Helvetic nappes that can be exemplified by the sketch on the top right corner, where we can see the different nappes, overturned and recumbent folds, stacked on top of the basement massif that are in the southeastern area the Aiguille Rouge and the Mont Blanc Massif. In summary, we can say that the Helvetic nappes represent the deformed sedimentary cover deposited on the European continental crust from the Permio-Carboniferous to the early Tertiary. They represent the last elements incorporated in the accretionary prism during subduction. In the Oligocene, the previously more distal ultra-Helvetic units overtrusted the at that stage still unfolded Helvetic domain over a distance estimated about 100 kilometers. After this event, two further stages of convergence were recorded. A first thin-skinned tectonic stage, producing faults with a wavelength on the order of 100 meters, associated with the thrust at the base of the nappes, with displacement on the order of tens kilometers. The resulting rock stack is composed by nappes that from top to bottom are in relation to their original paleogeographic position, that is from south to north. They are therefore characterized by a different paleogeographic origin due to a different distance from the European plate margin. As a result of this nappe stacking, the Helvetic sequence results repeated several times in the Rawill depression, as reported in the bottom left corner sketch. From the lowest northernmost para-autochthonous nappes, reported in green in the sketch, to the highest southernmost more allochthonous nappe, reported in yellow in the same sketch. The second stage of compression started in the early to middle Miocene. The nappe stack was updomed and folded on a large scale, about 10 km across, with an amplitude that is related to the crustal scale thrusting. This stage was associated with rocks cooling related to the progressive exhumation of the Alps. The axial depression of this large antiform has its structural lowest point in the Rawill Pass region, resulting from differential basement uplift along the antiform axis, the Aiguille Rouge and Mont Blanc Massifs southwestward, and the Haar and Gaston Massif northeastwards. So the Helvetic nappe structures are the result of two different compressional events, a thin-skinned tectonic followed by a thick-skinned updoming. These two different structural styles of these two compressional events reflects a gradual change from a thin to thick-skinned tectonics related to a deeper thrusting involving the basement. This scenario is summarized by these pictures that are the geological map of the area northward of the Rhone Valley, the 3D sketch of the antiform, the two cross-sections at the edge of the antiform, the area where we are going to focus the attention. To better appreciate these structures, we can move eastward along the Rhone Valley for several kilometers until the town of Martigny, where the river Rhone sharply bends northward along the Rhone Valley strike-slip fault. Here we can observe at the top of the mountain ridge on the right flank of the valley the spectacular outcrop of the Dent de Morgue Peak, where the result of the piling is very well shown. The complexity is well illustrated by the picture on the bottom left corner, where the relative younger tertiary flysch in yellow are between the underlying Jurassic blue carbonate rocks and the overlying green Cretaceous carbonate folded rocks, both older than the tertiary flysch. Let's go back to our area of interest and to the Schrattenkalk Formation outcrops that belong to the so-called Wildhorn nappe. On the basis of the available studies, this area is affected by the presence of 4 fault sets. A set of old Cretaceous normal fault striking northeast, and 3 sets of Neogene transtensional faults striking respectively north-northwest, west-northwest, and west-southwest. Zooming on our area of interest, we can recognize 3 out of these 4 sets. 2 sets are interpreted as Neogene transtensive faults. The first one oriented north-northwest, and the second one oriented west-northwest. The third set is instead interpreted as older Cretaceous normal faults oriented northeast. The third Neogenic set, the orange ones oriented west-southwest, is mainly present more southward, close to the Rhone Valley, and far from this area. To better understand the geological context, let's give a look to 2 northwest-southeast cross-sections, edging westward and eastward our area of interest. They well illustrate the structural complexity and the role of the different fault sets. The Paleo-Sedimentary Cretaceous faults, the hologenetic thrust confining the different nappes, and the Neogene oblique normal faults that are related to the progressive exhumation of the nappe stack and their large scale-up doming and folding. The blue arrow illustrates about the projection on the cross-section of the area of interest here on the western cross-section, and here in the eastern cross-section. The outcropping pavement of the Schrattenkalk Formation are dipping southeast-west-eastward, following the flank of the mountain affected by 2 blunt anticline and syncline. So, focusing on these 3 sets of faults, we can start with the Cretaceous one. These sedimentary Cretaceous faults are by far older than the formation of the Alpine fold and thrust belt, and typically strike southwest-northeast, parallel to the future Alpine fold axis. Here, the Haut-Froid Paleo faults, very close to our area of interest, is an example. These events may be related to post-breakup extensional tectonic along the European margin. In fact, during Cretaceous time, the area of the future Helvetic nappe was part of a large ramp-type carbonated depositional system of the European margin. The area of the Wildhorn nappe was transitional southeastward to the more distal and relatively deeper ultra-Helvetic basin. The Wildhorn nappe in fact includes a Cretaceous succession bearing clear evidence of this sedimentary northeast-southwest striking normal faulting. The evidences are lateral variation southwest-eastward in thickness and facies, with discordant contact corresponding to paleo-escarpment slump faults. In particular, the sedimentary normal faulting determined the disruption and exhumation of a Schrattenkalk platform, with the event of karst erosion on topographic high and sedimentation in topographic lows. Consistently, it is recognized the presence of Neptunian dikes mainly striking northeast-southwest. Here example of karstic dikes into Schrattenkalk Formation filled by sediment of the overlying Garcella Formation and by brecciated Swin Formation pelagic deposits. Let's move to the Neogene transtensive faults. These faults are younger than the Alpine fold and thrust structures related to the nappe stacking, and in general, they also cross-cut rather than reactivate the synsedimentary Cretaceous faults. The fault bordering westward our area of interest is referred to the north-northwest set, and this specific fault is named as the Wildhorn Fault. It is described as a normal oblique fault that accumulated an offset of about 300 meters on a 3 km fault length, cross-cutting the whole Cretaceous sequence and transecting both pre-existing Cretaceous synsedimentary faults and Alpine thrust. The fault contact with the Schrattenkalk Formation, where the fault juxtaposes limestone against limestone, is characterized by cataclasitis invaded by precipitated calcite, so representing, in a hypothetic reservoir, a permeability barrier. The fault bordering eastward our area of interest is referred to the west-northwest set, and this specific fault is named as the Efficiency Faults. It is characterized by a well-defined principal slip surface with a fault length of about 12 kilometers and displacement on the order of about 1 kilometer. The fault zone is generally represented by a quite localized area of deformation that cross-cut without significant reactivation both Cretaceous synsedimentary faults and Alpine fold and thrust. Millonitization and recrystallization are typically processes affecting the relatively poor shallow water limestone of the Schrattenkalk Formation where they are involved in the fault zone. Millonites at the contact are up to 1.5 meter thick, so representing, in an hypothetical reservoir, a permeability barrier. Veins, that means cemented fractures, are distributed in an echelon pattern developed as a precursor to more localized faulting. Let's now focus the attention on the fractures. Veins, that are fractures filled by cements, are very common in the Rawill area and developed throughout the deformation history of the Helvetic Nappes Formation. They are very frequent in the limestone beds of the Schrattenkalk Formation, as can be observed on the outcrops along the southern flank of the Schneiderhorn Peak, where they represent a very close network. Of course, on this kind of pavement, where we can walk on the top of beds dipping about southeastward, fractures are exposed to the severe high-altitude weather condition that have enlarged by dissolution the fracture's aperture. Although we have to remember that the fracture's aperture in a buried reservoir are in the order of few hundreds of microns meter, this outcrop view gives us the opportunity to appreciate at large scale how the fracture's intensity could be close with the interfracture spacing in the order of few centimeters. So we can take advantage of this condition to appreciate the fracture intensity that can affect a reservoir. Actually, the available studies have recognized the presence of different veins in relation to timing, mode of formation, and degree of deformation. Some sets of veins are estimated to be synfolding, linked to the formation during nap emplacement, mainly parallel to bedding or foliation, cross-cut by stylolite, compacted, sheared, or boudinaged. Some other sets of veins are estimated as post-folding, coeval with the later neogene transtensional folding during exhumation and updoming. These later sets are characterized by sheared veins linked to folds in an echelon arise. All these veins are very intense along the fold zone, with a quite chaotic orientation, and are very often cemented. However, close to the folds, veins' orientation and shape can be influenced by the interconnection with the fold planes, by rotation in the fold damage zone, so that the currently measured opening direction can deviate from the regional trend. They represent examples of how fracture can sometimes represent in hydrocarbon reservoirs permeability baffles or even barriers rather than enhanced flow paths. Although some fractured reservoirs are strictly linked to the fault zone, however, very often in a fractured reservoir, the storage capacity and flow capacity of the fracture system is more linked to the fracture network, affecting the bulk volume of the filled rock, that is, very often far from the fault zone. It is therefore the description estimation of the mode 1 veins affecting the country rock that generally define the reservoir characteristics. Therefore, being the target of this virtual field trip, people involved in a fracture reservoir study, we focus the attention on these mode 1 fractures that, very widespread in our area of interest, occur far from the fault zone and record the regional stretching direction during their opening. These mode 1 fractures are estimated to be linked to the neogenous transtensional folds and have been separated into 3 distinct sets on the basis of their opening orientation as defined by the direction perpendicular to the walls: north-northwest striking, west-northwest striking, southwest striking. The cross-cutting vein relationship and the change in tip orientation have been interpreted as suggesting a progressive relative rotation counterclockwise of the stretching direction from west-southwest toward south to south-southeast for these post-faulting veins. These extensional fractures have been related from the published studies to the neogenic folds representing the latest evolutionary steps from nap stacking ductile behavior due to the several thousand meters burial depth inside the accretionary prism with the condition of high temperature and pressure to the brittle behavior of the post-nap doming and transtensional faulting due to exhumation and rock cooling. However, we wonder if some of the southwest striking veins could not be also a kind of heritage of Cretaceous age strain, as well as we wonder also if all the veins could not represent a kind of heritage of the naps folding, especially considering that in the most northern area of the Helvetic naps, corresponding to the outcrops considered in this field trip, no significant metamorphic event have been recorded, and therefore a more brittle behavior could not be ruled out also in the nap stacking phase. Going closer to the outcrops, we can see from an aerial view that in between the large fold before mentioned, a by far larger number of decametric fold fractures can be recognized. And even more when we walk on top of the outcrops. From this image we can infer how the fracture intensity can be high in a reservoir and how the selective dissolution of the cements in filling the fractures, here mainly affecting the fracture striking west-northwest, about parallel to the Iphigan Sea faults, can drastically make the anisotropy of a possible reservoir very high. Let's try to summarize from a reservoir study perspective a fracture set of different vintages present in these outcrops of the Schrattenkalk Formation. We have the old Cretaceous fractures relevant to the extensional sedimentary faulting linked to the Tethys opening. Despite being significant events, they are likely to be not very effective, being infilled by the sediment of the overlying younger formation as a kind of Neptunian dikes. The enfolding fractures related to the fold and thrust belt of the Helvetic nappes. Despite the huge strain and stresses of this tectonic event, the rocks, buried at high depth inside the accretionary prism in conditions of high pressure and temperature, were very ductile, not prone to fracturing. The post-folding fractures relevant to the Neogene transtensional faulting, linked to the exhumation of the nappes characterized by the updoming and folding at a large scale. The resulting fracture network is very close and complex, as shown by the outcrop of the Schrattenkalk Formation, where the presence of the fracture is highlighted by the weathering dissolution that give us an idea about the possible scenario that we could face in some buried fractured reservoirs. In front of this complexity, it is clear that when we deal with a buried reservoir, our ability to predict the reservoir production performances before the field is brought on stream is very often fanciful and visionary. In fact, the granularity of the data generally available makes our knowledge totally inadequate to make both a reliable reconstruction of the fracture network and its characterization. This because of the intrinsic characteristics of the fracture network that is very discrete and discontinuous, exacerbating the shortage of the available data. Just as an example, let's look at this horizontal outcrop. We can recognize the presence of different fracture sets. Two sets are perpendicular to each other, 1 and 2, and both generally closed because affected by the white cement infilling, while the other two fracture sets, one parallel and one oblique to the other two, are open, not cemented events. The former two sets are likely to represent permeability baffles to the flow, while the latter two are likely to increase the permeability and anisotropy of the rock matrix. However, the actual characteristics in terms of flow behavior of this rock is defined by the interplay of these different fractures at a larger scale. Now, let's envisage to drill and core 3 wells at a very short distance. We can understand how the data collected from these very close vertical wells can be very different, inadequate, misleading, unable to capture the actual complexity. Considering the rock volume investigated by these vertical wells, we can realize how the data collected are bound to be different, despite the very short distance, and inadequate to have a real picture. In case of the well located in the fracture interspace that exceed the well diameter, a not fractured rock scenario would be inferred. A pessimistic scenario would be instead inferred by the well just located 1 meter apart and intersecting the cemented fracture sets, or an optimistic scenario by the well intersecting just the open fracture sets. But the real impact of these fractures on the rock permeability is related to the interplay between these fractures that is likely controlled at larger scale by the segmented fractures, stopping the continuity of the open fractures. So when we face the study of a fractured reservoir, an important starting point is the awareness of the need of a geological interpretation and integration of the data collected from the drilled wells. Otherwise, the risk is to build a fracture model that just describes statistically the data, a geometric model rather than a geological model. The awareness of the uncertainties at stake is always a good starting point for the fracture study. Only after the field production startup and the record of a significant production history, a significant volume of the reservoir will be investigated and the calibration of the role of the fractures could be performed to optimize tune the initial geological interpretation. Only with this additional data at larger scale, a reliable description and characterization of the fracture network can be performed. To investigate more in depth the issues of the fracturing in the shaft and calc formation in the Rawill axial depression, a good base camp could be the Wildstrubel hut, from which enjoying a nice view of the Rawill Alpage and the sunset on the overland Pernes. Here you can find a short list of papers to refer to if you are interested in investigating more in depth the geology of this area. Let me conclude with a consideration trivial but not obvious. Before building a reservoir fracture model and performing its calibration with the dynamic data, it's very important to try to get a geological understanding of the structural history affecting the reservoir. This understanding is basic to build a fracture model that is not just a geometric representation of the fracture recognized in the few drilled wells.